Welcome to Shanti-Peace for Mathematics. This video gives an idea regarding the two objects, especially a curve and the surface. They play a very important role in the study of partial differential equation. Let us see what is the curve in a space. When I can say a space, it is a three-dimensional object. So all the things we are discussing in R3. A curve may be a specified mean of a partial parametric equations. Suppose that f1, f2 and f3 are two continuous functions of variable t, which varies in the interval I, which is a subset of R. Then the equations x is equal to f1 of t, y is equal to f2 of t, and z is equal to f3 of t, where t belongs to I, represents a parametric equation of a curve in three-dimensional space. Represent parametric equation of a curve in R3, or I can say a three-dimensional space. A standard parameter is the length of the curve measured from the sum point of the curve. In such case, at a time, the symbol s is used instead of t. So many times this instead of t, a standard symbol is used for s, which is known as a length of the curve. Note that the condition that the parameter t is of length of the curve is f dash square plus f1 dash square plus f2 dash square plus f3 dash square equal to 1, where this prime will denote the first differentiation of the function f with respect to t. Let us give you examples of curve in R3. A simplest example I can give a curve is a line. So as we know, a line with the direction cosine is LMN and passing through the point x0, y0 and z0. The parametric equation, or in general we know that the Cartesian form of this line is x minus x0 by L equal to y minus y0 by M is equal to z minus z0 by N. And if I call this as some parameter k, or as per the previous notation, if I can say it is t, where t belongs to any number in R, then x I can say it is in the parametric form. I can write down x0 plus lt, y equal to y0 plus mt, and z is equal to z0 plus nt, where this t is any real number you can take. So this is the, I can say, a parametric equation of a straight line. Let us give you another example that is known as a circular helix. So first of all, you should know what do you mean by a right circular helix. So what is the meaning of a right circular helix? So if you have a circular cylinder like this, and on this cylinder if you have one curve is situated in this manner, this is known as a right circular cylinder. This curve which we have here, so the curve is of this type, is like a spring. It is like a spring which we are playing in our early age. So this is the situation, or this is the figure, or this is the curve, a right circular helix. What is the equation of the right circular helix in the form of parametric form? That is, x is equal to a cos omega t, where t is a variable, omega is a fixed constant, and a is also a fixed constant. Y is equal to a sin omega t, and z is equal to kt, where t is a parameter. I can say it belongs to R, and a, omega and this k are constant. So this is about a curve. So there are many other curves you can plot. For example, if you want to write down the equation of the circle, then maybe in your graduation you have learned that the equation of the circle can be written as either it is an intersection of two spheres, or a sphere and a circle, or it will be an intersection of a cylinder and a plane parallel to that. So there are different ways to represent the circle so circle is a curve in R3, and which can be expressed as intersection of two surfaces. So before that, to understand what you mean by surfaces, let us give certain idea regarding the surfaces. So surface, a point xyz in a space is said to be lie on the surface if the coordinate x, y and z satisfies f of x, y, z equal to 0, where f is continuously differentiable function. Defined on domain in R3. So any equation which satisfies this type of equation, it is known as a surface. Therefore, surface is a locus of the point moving in a space with the 2 degree of freedom, because this is the equation where we have x, y and z, 3 parameters are involved, and one of the parameter depends on the other two. So whenever you want to say a surface is a locus of the point moving the space with the 2 degree of freedom, and this idea leads to that a parametric form of the surface can be represented in the form of x is equal to f1 of uv, y is equal to f2 of uv, and z is equal to f3 of uv. Then for each pair of value u and v, their corresponding 3 numbers x, y and z, and hence the point x, y, z, it is in the space R3. However, it is not true that every point in a space correspond to a pair uv. If the Jacobian, that is Jacobian, the notation is del f2 upon uv will be del f1 upon del u, del f1 upon del v, del f2 upon del u, and del f2 upon del v, which can be simplified as del f1 upon del u into del f2, del f1 del v, and del f2 del u. If this Jacobian is non-zero, then the first two equations of this equation 1, the first two equation of 1, first two equation of the 1 can be solved to express u and v as a function of x and y locally. Say u is equal to lambda of xy and v equal to mu of xy, and this is true by inverse function theorem. And this means that u and v can be determined once x and y are unknown. And the third equation, that is z is equal to f3 of xy, is also can be determined using the value by putting this value of x, that is lambda of xy, and so that f3 can be calculated as lambda of xy mu of xy, and so the value or the parameter z can be calculated, and thus the any point xyz can be determined on using the equation 1 on the surface, and this is known as a parametric equation of the surface. The parametric equation of the surface is not unique. It may be a different into the different example. So I am repeating again this line. A parametric representation of a surface will not be unique. It may be a different with a different example. For example, I can give you one example here, that is example of a sphere, that we know that the parametric form or Cartesian form of the surface x square plus y square plus z square is equal to a square. If you can write down into the spherical coordinates of this, then it will be a is equal to a sine u cos v, y is equal to a sine u sine v, and z is equal to a cos u. This is a parametric form of a surface x square plus y square plus z square is equal to a square. This is the one way is to represent as a parameter. The another way is to represent a same equation as x is equal to a into 1 minus v square upon 1 plus v square into cos u. Y is equal to a into 1 minus v square upon 1 plus v square into sine u. And z is equal to 2a v upon 1 plus v square. If you make a square plus b, x square plus y square plus z square, it will give me a square. You can check. Where here the a I have treated as a constant. And both these equations represent an equation of the sphere like this. So the conclusion we can make is the parametric equation of the surface is not unique. It is different with a different example. Now let us go back to the equation of the curve. Equation of the curve is f of x is equal to f of f1t, y is equal to f2t, and z is equal to f3t. On eliminating t from the first two function, we'll have the relation that is phi of xy equal to 0. Similarly, if I eliminate t from the second two equation, then we'll have equation xi of yz equal to 0. And hence the curve, as I told you, can be represented as a point of intersection of the two surfaces. This will represent the surface in 3 dimensions. This is also represent the surface in the 3 dimensions. So intersection of the two surfaces, it will also gives you a curve. As I have taught you, or I have told you regarding this, that x square plus y square plus z square equal to a square is one of the sphere is there, and if I intersect this sphere with the plane x is equal to 0, then it will gives me one circle whose center is origin. And in likewise, any two surfaces are there, intersection of those two surfaces will gives you a curve in general. If the parameter s in the equation of the curve is the length of the curve measured from the fixed point, then dx by ds, dy by ds, and dz by ds represent the direction cosine of the tangent to that curve at the point C. So let me write this as a note here, that this del x, not del, but it is dx by ds, dy by ds, and dz by ds are the direction cosine of the tangent to the curve at that point, at the point S. To the curve means, here the curve means x is equal to f1 of s, y is equal to f2 of s, and z is equal to f3 of s. This is my curve. Suppose that the curve C is x of s, y of s, and z of s, is the curve is given to you, which is lies on the surface S, whose equation is f of xyz equal to 0. Then actually what we get is f of x of s is 0, f of x, f of ys, f of zs equal to 0 by substituting the value of x here, y here, and z here. For every s we have this. On differentiating both sides with respect to s, and as you know, this f is a function of 3 variables x, y, and z, and this x, y, and z are the functions of s. And if I use the chain rule and I find differentiating with respect to s, this will leads to del f upon del x into dx upon ds. If I go via this path, then we will have plus del f upon del y into dy by ds plus del f upon del z into dz by ds equal to 0. This condition gives you a relation between a direction cosine. I already talked about the what is del x by del s, del y by del s, and del y by. So this actually I can write down as del f by del x, del f by del y, del f by del z into dx by ds dy by ds. So it is a dot product of two vectors, I can say. And what is this represent? It is a direction cosine of the tangent to the curve C. Hence, the dot product of this two is 0. What will be this represent? It will be the line which is perpendicular to tangent to the curve. So suppose this is the situation you have. This is the surface you have. On this surface there is one curve. This is the curve C. And on this curve C, this is your tangent at this point. Let's say this is the tangent to the curve. And what is this represent? A dot product of this direction cosine with the 0. That means this, whatever the line whose direction cosine is this, will be 0. That means this two line will be a perpendicular line. So this line is perpendicular to this line. And the direction cosine of this line is this del f upon del x, del f upon del y, and del f upon del z, which is actually a perpendicular to tangent to the curve, or I can say perpendicular to the tangent line to the curve. And so the direction of this one will gives you a normal. So this is actually a direction ratio of the normal to the surface at the it will gives. And that is also another way is to looking at this is a gradient of the function f. If you have learned regarding the vector calculus, in that this is known as a gradient of the function. So again I am repeating, this gradient of f is represent a normal to the surface at the point P, a direction ratio of the normal to the surface at the point P. That's it for this video. If you like this video, please press the like button. If you have any comment, suggestion or question, please drop down in the comment box below. See you in next video. Till then, bye bye, sayonara.